Welcome to the third lecture of our high performance computing course. Today we'll continue looking at basic computer organization, and you'll recall from the previous lecture, which I'll quickly review what we looked at as far as organization is concerned, that there are three main parts to a computer system. They are the processor, the main memory, and the I/O devices, and we saw that all three are extremely important. We're going to spend some time talking about processors and main memory, not so much about I/O devices, but I'll make a few comments about them. Now, one of the important concepts as far as programs are concerned, as we saw in the first lecture, our C program gets compiled, translated by a program called a compiler into an equivalent program in a language that is understandable to the hardware. That language is called the machine language. And the simplest instructions, the simplest operations in the machine language are known as machine instructions. So ultimately, the C program that you write is translated by a compiler into an equivalent program in which the algorithm is described in terms of a number of machine instructions. The machine instructions are understandable to the processor, which executes the program. And a simple example of a machine instruction is an instruction to add two unsigned integers, let us say. Now, as far as a given processor is concerned, I will use the term instruction set to refer to all the different kinds of instructions that particular processor is capable of executing. So with these basic terms, if you look back at our diagram of the organization of a computer, the building blocks of a computer, we understand that the processor or CPU is the most important box, the most important component. But the memory is also extremely important, because that is where the instructions of your program and the data of your program are remembered, and therefore the memory is essential and very important. Finally, the I/O devices in turn are important because it's only through them that interaction with the outside world happens. Finally, there must be some interconnection between all of these components, and that I show in this diagram in the form of something called a bus. And communication between the memory and the CPU, or between the I/O devices and the memory, would happen possibly through this bus. Now, we are going to spend some time looking into the components of the processor, and the three important components of the processor that we will look at are the ALU, the registers, and the control unit, which are shown in the small boxes inside the large box that you see in this diagram. Okay, now among these, the first and the easiest to understand is the control hardware. Now, the word hardware is used to indicate that what we're talking about here is some form of electrical circuitry, electronic circuitry. And basically, the control hardware is the electrical circuitry, electronic circuitry that manages or controls the instruction execution. And this would be of great interest. The details of the design of control hardware would be something that you would study in a course on electrical communication engineering, or a course on computer science and engineering. Now, the second box that we saw inside the CPU or processor was something which was labeled ALU. And many of you would know that this is the abbreviation for arithmetic and logical unit. As the name suggests, this is again a piece of hardware, circuitry, that is capable of doing arithmetic and logical instructions. In other words, doing the calculations or the logical operations necessary in order to achieve what the instructions require. For example, if there is an add instruction which is capable of adding unsigned integers, there would be a corresponding circuitry inside the ALU, which would be called the unsigned adder, which could do the operation. Finally, there's a unit in the box called registers. And this may be a new term to many of you. So let me explain. The registers are small units of memory, and they are used to hold data or instructions temporarily during the instruction execution. So remember, all three of these are parts of a processor. Now, there's a little bit of ambiguity here, because as you'll see, I have used the word memory over here in a different way from what I had used it in the previous slide. In the previous slide, where we had the diagram, I had this box labeled memory, and I was indicating that this is a component of the computer system where instructions and data are stored. Whereas over here in this slide, I'm using the word memory in a slightly different way. So what you should understand from this is that the word memory, unless disambiguated, could mean a few things. I'll therefore spend a little bit of time explaining what memory is and what and I'll be a little bit more careful in my terminology when I talk about memory from now on. So let's try to understand about memory. The first question you'll ask is, what is memory? And in the abstract sense, you would recall that you yourself have memory. You are capable of remembering things. Therefore, somewhere in your system, there is something that is capable of remembering. And in general, you might say that something that can remember things would be called memory. There's memory in the human beings. There's various forms of memory in a computer system, and so on. Now, just to be a little bit more specific, you as a human being remember things in your system using part of your brain or wherever else the memory may happen. But you also use other mechanisms to remember. For example, in preparing this lecture, I made lecture notes. And I made the lecture notes on pieces of paper. So as far as I'm concerned, the pieces of paper with something written on them serve as a form of memory. And there are various other forms of memory that a human being makes use of. But what about in a computer system? In a computer system, as it happens, there are many different kinds of memory. In other words, things that can be used to remember. And the box which I had labeled as memory in the block diagram of a computer system is one very special kind of memory. We're now using the word memory in the more general sense. So let me just say something about the different kinds of memory in a computer system. Now, I'm going to distinguish between the different kinds of memory in a computer system based on the kind of circuitry or the mechanism that is used to do the remembering. I used the example of how a human could remember on a piece of paper by writing something on a piece of paper. As it happens, in computer systems not so long ago, paper was used as a form of memory. Some of you may remember or may have heard of how people used to type programs. They didn't type programs in at a keyboard. They actually used to type programs onto pieces of cardboard. Right? And this deck of cards would then be fed into the computer. And therefore, the paper, the cards, the computer cards, were a form of memory. Similarly, there was a time at which paper tape, spools of paper tape, in which holes were punched at well-specified locations, were used as a form of memory. Paper is hardly used for memory in computers anymore. But it's interesting to note that historically, paper was an important form of memory in computer systems. In today's talk, I'm not going to use paper as an example in the slide because it's actually not that common anymore. So I'm going to distinguish between the different kinds of memory in a computer system based on how the remembering is done, how the data that is to, or instruction that is to be remembered is remembered. So in that sense, I could say that in a computer system, there are some forms of memory which do the remembering by the state that an electrical circuit is in. So there could be carefully designed circuits which could be in, let's say, one of two states. And if the circuit is in the state which is called 0, then it might be remembering the bit 0. Whereas if the circuit is currently in the state called 1, then I might say that I'm remembering the bit 1. And by having a huge collection of such circuits, I can remember entities which are larger than 1 bit. So that's the general idea of this form of memory. The idea that I could have electrical circuits which are capable of remembering, and the remembering basically happens by the state that the electrical circuit is in. In other words, the current situation as far as the electrical circuit is concerned. And just to give you one simple example of a memory in a computer system which is of this form, some of you may have heard of something called static RAM, and I'm going to talk about parts of a computer system which use static RAM later. Up to this point in time, we have not seen a part of a computer system which uses static RAM. But static RAM is an example of a device of the first kind. Okay, now there are other memories in computer systems which remember not by the state an electrical circuit is in, but by the amount of charge present in a capacitor. A capacitor is a kind of a component in electrical or electronic circuits. And if memory is implemented using the amount of charge on a capacitor, the situation might be that if there is no or low charge, that would be the equivalent of remembering a 0. And if there is high or a large amount of charge, then that might be the equivalent of remembering a 1. And an example of a memory which is used in computer systems which is of this kind is something known as dynamic RAM. And in fact, the memory block which I had used in the block diagram of computer organization typically uses this kind of memory. In other words, the remembering of data and instructions is actually happening through the amount of charge in various capacitors inside the memory device. Okay, now a third kind of remembering which happens in computer systems today is that information could be remembered by a magnetic or optical property which is used. And I think many of you can remember situations where this happens. For example, as far as magnetic properties are concerned, you know that there are the hard disks which you have on most computer systems today actually remember by the magnetic mechanism. If you were to open a hard disk, you would find out that there is something like a plate which is coated with a magnetic material, and that there are different sectors, different regions on this magnetic surface, and those are basically the different bits of storage. So a hard disk remembers through magnetic properties. And all of you have used VCDs or DVDs and may be aware that these operate through the optical properties of the medium. So examples of remembering by magnetic or optical properties are things like hard disks or magnetic tapes. Some of you may have used tape cartridges in systems that you have access to. And finally, VCDs or DVDs. So these are all examples of the third kind of remembering. Now, if you look at this range of possibilities that I have outlined over here, the SRAM, the DRAM, and the optical or magnetic storage, obviously they differ in some way from each other, and very clearly they differ in terms of how the remembering is done. But there is another critical component in which they vary, and that is they vary substantially both in their speed and in their capacity. And what I mean by speed here is how fast one can read something, a piece of data or an instruction out of that memory, or how fast one can write a new instruction or data into that form of memory. So that's what I mean by speed, the speed of access. And what I mean by capacity is the amount of memory that one can have in, let's say, a given area or for a given amount of money. And as you know, 1 gigabyte of storage on a DVD is much, well, let me put it this way. If you are into purchasing computers or into making decisions about the purchase decisions as far as the computer is concerned, you would be aware that it is much cheaper to add 500 gigabytes of disk into a computer system than to add, let's say, 4 gigabytes of main memory of the DRAM type into a computer system. Right? So disk is very clearly much cheaper than, in terms of its cost per a given amount of storage, than the main memory is, the DRAM memory. And VCDs, DVDs are clearly much cheaper than the disk. So that's what I meant when I had in the slide the indication that the memories that we saw can vary substantially in their speed and in their capacity. Therefore, we expect that in a computer system we may see a lot of storage which is of low cost and not that much storage of high cost, and that we expect that the storage which is of low cost will be therefore of high capacity and is likely to be much slower than the storage which is of high cost. Therefore, there's clearly going to be some kind of a trade-off that has to be played. So with this quick aside about memory, let's go back to our discussion about computer organization. I'll move on to the next slide. Now in the next slide, you'll recall that I said that there are 3 important components to the processor. They are the control hardware, the ALU, and the registers. And I had indicated that the registers are small units of memory, and they are used to hold data or instructions temporarily during execution. So registers are a form of memory. They are small because they are inside the CPU, right? And if you have too many registers, then there may not be enough space in the CPU for the other important parts of the CPU, like the control hardware and the ALU. But from now on, we will use the term registers to refer to this use of memory inside the CPU. And let me just say a little bit more about registers. Okay, so registers are an important part of the processor. And there are 2 main kinds of registers which are used in a CPU. They are known as the special purpose registers and the general purpose registers. Let's look at each of these in a little bit more detail. First of all, let's look at the special purpose registers. Now, as the name suggests, the special purpose registers are small pieces of memory which are inside the processor, and they are used for specific purposes by the control hardware. That's why they are called special purpose registers. They are used for specific purposes, and each of the special purpose registers would be known by a name which is indicative of the specific purpose for which it is used. I'll give you 2 or 3 examples, and these examples are going to be critical for our discussion of the processor which is to follow. Now, one of the very important special purpose registers in any processor is a special purpose register which is known as the program counter, which is typically abbreviated as PC. And this is a register, a special purpose register, that is used to remember the location in memory of the instruction which is currently being executed. You will remember that at any given point in time, the processor is executing an instruction, and that instruction came from memory. Therefore, the purpose of the program counter is just to remember from where in memory the current instruction which is currently being executed came. That's all. So there's a special register called the PC or program counter for this purpose. There's another special purpose register called the instruction register, or IR, in the CPU, and this is used to remember the instruction that is currently being executed. So you think of the instruction register as a small amount of storage inside the CPU, which at any given point in time contains or remembers the instruction which the CPU is currently executing. And this may be necessary because in executing an instruction, the control hardware may have to examine that instruction in great detail, different parts of the instruction, and therefore the instruction register is the place in the CPU where the instruction is located. As one more example, most processors will have either one or a collection of registers which are used to remember status information about the current state of the processor, and this might be known as the processor status register. What I mean by the current state of the processor could include many different pieces of information. One of the pieces of information might be, for example, just after an arithmetic instruction has executed, there is the danger that during the execution of the arithmetic instruction, an arithmetic overflow may have occurred. And if that is the case, that could be reflected as a change in the state of the processor by maybe a bit in the processor status register. So various pieces of information about the current state of the processor would be contained in this processor status register and used by the control hardware to manage the execution of a program. Remember, the control hardware, the ALU, and the registers are the 3 parts of the processor. We are currently looking at some of the registers which are known as the special purpose registers. Let's now move on to the second kind of register, which is the general purpose registers. Remember, of the registers in the CPU, some are special purpose, which are used for special purposes by the control hardware. Others are general purpose registers. As the name suggests, these are registers which can be used for anything that the programmer wants. So they are available for use by the program. They are not used for special purposes by the hardware. They are available for use by the program. Now, typically as programmers, many of us are not even aware of the fact that there are general purpose registers. So this may come as a little bit of a surprise. The idea that there are registers, pieces of memory inside the CPU that I as a programmer can make use of. Now the interesting thing to note here is that as a C programmer, even if you are not aware of the fact that there are general purpose registers, it doesn't matter because you write a program using variables in C, and this program later gets translated by a compiler into a language called the machine language. So as long as the compiler knows about the general purpose registers and uses them while translating your program, then your program will be making use of the general purpose registers. But sophisticated programmers who like to make their programs as efficient and fast as possible may want to try to make use of the general purpose registers explicitly. Okay, so the question which may arise now is, okay, so there are registers in a processor, in other words, small pieces of memory inside the processor, which are intended for whatever use the program wants to make of them. And typically what these registers are used for by the program is for remembering frequently used data. So if there is a piece of data like a variable x which your program is using, which is accessing many times, rather than accessing that variable out of memory every time, the program may want to access it out of a register, because the register is part of the processor itself, whereas the memory is a separate block in the organization of the computer. Okay? So we may want to get a better idea about why this is a good thing to do. So why is it a good idea to put frequently used data into a general purpose register rather than just leaving them in memory along with all the other data? Okay, now this is an important concept, so I'll spend a whole slide on trying to make sure that this is clear. The question that we're trying to answer is, we know that general purpose registers are available in a processor for whatever purpose the program wants to make of them. And I indicated that they might be used for storing frequently used data. But why is this in the interests of the programmer? Why is this in the interests of the good execution of the program? Now the reason that this is a good idea is that there is a large speed disparity between the processor and the memory where the instructions and data are stored. Now from now on I'm going to refer to the memory where the instructions and data are stored, in other words that block in the computer organization block diagram, as the main memory, because that is the critical memory of the computer where the instructions and data are stored. So apparently there is a large speed disparity. In other words, the processor and the main memory operate at completely different speeds. Let me give you an idea about how fast or how slow they are relative to each other. Now let's think of the case of a 1 gigahertz processor. You may have heard of this kind of a quantification of the capabilities of a processor in computer ads or manuals and things like that. Now what we have over here is a quantification of, I pronounced that 1 GHz as 1 gigahertz. We've come across G before. In one of the earlier lectures I mentioned that G is an abbreviation for something. We haven't come across HZ before, but some of you may have come across HZ in a course in physics. Hertz is a measure of frequency. So our suspicion is that this is a measure of the frequency of a clock used in the design of the processor, or in some sense a measure of the speed of the processor. So if 1 gigahertz quantifies the speed of the processor, it also quantifies in some sense the time scale of the processor, the amount of time in which something important happens inside the processor. So 1 gigahertz is actually 1 billion cycles per second. So I can easily convert from frequency to time scale by just taking the inverse, and if I do that, what I come up with is the idea that a 1 gigahertz processor actually has a time scale of 1 nanosecond. And before going any further, let me just clarify what's happening here. Now, first I'll come back to the gigahertz shortly, but first of all, what is this nanosecond? I haven't used the term nano before. Some of you would have encountered it before. We talked about kilo, mega, giga, and so on. There's also milli, micro, and nano, and as you all know, milli is 10 to the power minus 3. For example, a millimeter is 1,000th of a meter. A micrometer is 1 millionth of a meter. A nanometer is 1 billionth of a meter, or 10 to the power minus 9 meters. So a nanosecond is 1 billionth of a second, or 10 to the power minus 9 seconds. Now in the previous lectures I had talked about G as standing for 2 power 30. Now that is not always what the abbreviation G stands for. In computer systems, if I am talking about memory, the size of memory, then G stands for 2 power 30. So if I am talking about a gigabyte of memory, that is 2 to the power of 30 bytes of memory. But if I am using the G, the prefix G to refer to frequency or the size of data on a disk, then G actually stands for 10 to the power of 9. In other words, it's a metric, the metric quantity. Therefore, the 1 gigahertz that I referred to in terms of the power of the processor is a billion hertz, a billion cycles per second, whereas a gigabyte is 2 to the power of 30 bytes of memory. Similarly, as far as disk is concerned, a 500 gigabyte disk contains 500 billion bytes of information and can contain 500 billion bytes of information in it. So this is how I came up with this quantification of the time scale of the processor, that a 1 gigahertz processor has a time scale of 1 nanosecond. What does it mean to have a time scale of 1 nanosecond? Once again, that basically means that in a processor, an event of interest happens in about 1 nanosecond. Okay, now the next question which will arise is, how fast are the main memories that we have on computer systems today? Because my claim was that there is a large speed disparity between processors and main memory. As it happens, the main memories of today have a time scale of about 100 nanoseconds. That's an order of magnitude approximation. The time scales could be 70 or 90 or 110 nanoseconds, but it's approximately 100 nanoseconds. What does this mean? This means that the main memory is about 100 times slower than the processor. Right? So every time the processor needs to fetch an instruction from the main memory, it has to wait for about 100 time units in terms of its local time scale. And this is a fairly large speed disparity. The processor is about 100 times. A 1 gigahertz processor is about 100 times faster than the kind of memory that we're talking about over here. And as you well know, the processors that are available today are sometimes faster than 1 gigahertz, more powerful, with higher frequencies than 1 gigahertz. For example, some of you may even have 3 gigahertz processors in your desktop computer in the lab or at home. And that would mean that the time scale is 1/3 of a nanosecond. Right? So the situation that I've outlined over here is not an extreme case. The 1 gigahertz processor is very common. I mean, processors are typically faster than 1 gigahertz, and memories are not going to be much faster than this 100 nanosecond time scale. So this is the reason that using general purpose registers makes a lot of sense to the program and to the programmer, because the processor is 100 times faster than the memory, and therefore if you have data which is frequently accessed, and every time it has to be accessed, it is accessed out of main memory, that's going to take 100 times more than if the data had been present in a register, a general purpose register inside the processor itself, in which case it could have been accessed in an amount of time comparable to the time scale of the processor, a nanosecond or thereabouts. So this is the reason that using general purpose registers for storing frequently accessed entities is critical to the efficient execution of a program. Okay, now before going back to our discussion of computer organization, I thought it might be useful to just give you some kind of a feel of what this 1 nanosecond time scale of the processor means. Very few of us can actually visualize what a nanosecond is, because the human response time is so much slower than a nanosecond. Right? We are just like there's a large speed disparity between the processor and the CPU and the memory. There is an even larger speed disparity between the time scale of a human being and the time scale of the processor. This is an interesting thing to think about. What is the time scale of a human being? What is the amount of time that it takes to do the fastest operation that a human being is capable of? And you could try to estimate this using the examples from extreme human behavior. For example, you know that somebody who's an expert typist can type at, let's say, 100 words per minute. And from this you could calculate how much time it takes for the person to press one key. Or you know that somebody is able to run 100 meters in 9.5 seconds. From this you could calculate something about the human's time scale. But very clearly the human time scale is much slower than the time scale of either the processors or the memory. So to understand what 1 nanosecond is, we need some other phenomenon. So the phenomenon that I'm going to use is in fact light. Because when we talk about 1 nanosecond, we're talking about something which is actually on a scale where light, the movement of light is to be taken into account. Now you know that the speed of light is approximately 300,000 kilometers per second. And if a quick calculation on the back of an envelope will tell you that what this means is that light travels at about 0.3 meters per second. Per nanosecond. So a nanosecond is the amount of time that light takes to travel about this much distance. Right? Light travels about this much distance in a nanosecond. That's what a nanosecond is. If I have a 3 gigahertz processor, then the time scale of the processor is about 1/3 of a nanosecond, which means that light could travel about 4 inches, about this much distance. And we're now looking at a distance which is about the size of a large computer chip or a processor. And this may be a problem as far as designing computers is concerned. If the signal, if the flow of information in a computer chip is even 60% of the speed of light, then in the time scale of one of these fast processors, it's not going to be possible for a lot of signal flow to happen inside a large chip. So this is the significance of the nanosecond. Processors are quite fast, memories are slower, but processors are in fact so fast that designing high-speed 1 gigahertz, 3 gigahertz processors is itself an art, because one has to very carefully lay out the components inside the processor so that the speed of transmission of the signal does not become an issue. So with this we have a clear understanding that it makes a lot of sense to make use of general purpose registers as far as possible for storing frequently used data. So let's move on. We are talking about general purpose registers. We understand that they are available inside the processor, just like special purpose registers are, and they are useful typically used by the programmer or by the compiler on behalf of the programmer for remembering frequently used data. Now the question which will be foremost in your mind is, how many such registers are typically available in a processor? Because you are hoping that there are thousands and thousands of such registers so that you can make use of them and get the full benefit of this very fast access to the variables of your program. But unfortunately, a typical processor today has something like 32 general purpose registers. This is a fairly typical situation. There could be a few tens or at most a few hundreds of general purpose registers. And as I indicated earlier, this is largely because the space on the processor, the amount of area of circuitry that can be built into the processor, is not available only for general purpose registers. There's a lot of other critical functionality that must be included, and 32 has been found to be a good compromise between what is useful to the programmer and what is possible. Now if there are 32 general purpose registers in a processor, then they have to be individually referred to, just like I talked about the program counter being referred to as the PC, instruction register being referred to as the IR. Now the program counter as the instruction register are used by the hardware, and therefore the programmer in his program does not typically have a need to refer to the program counter or the instruction register. On the other hand, a programmer or a compiler will have to make use of the names of the general purpose registers inside the program. Therefore from now on, if I am referring to general purpose registers, I will use names like R0, R1, R2. If there are 32 registers in a processor, I might use the names R0 through R31 to refer to the 32 general purpose registers. And we would expect that in a program which makes use of general purpose registers, the name of the register, such as R0, R1, R2, etc., will appear. Okay. Now, typically when we have general purpose registers and we have main memory, what this means is that as far as a given instruction is concerned, the instruction takes operands, and the operands to the instruction could either come from a register or they may have to come from main memory. Remember, all the variables of your program, whether they are statically allocated, dynamically allocated, or stack allocated, are all going to be present in the main memory along with the instructions of the program. The instructions get fetched from the main memory into the processor as and when they're going to be executed, but the variables are present in the main memory, and if the program is written so that a particular variable, let's say the integer variable x, is copied into a register, then the value of the variable could be accessed from inside that register, and therefore an instruction which is to operate on the variable x could instead operate on the register which contains the variable x. So in general, the operands to an instruction could come either from registers or from main memory. So at this point, our picture of the basic computer organization looks like this. You've noticed that I've replaced the term memory in this block by main memory. From now on, whenever I refer to this block, I will use the term main memory, because we know that the word memory is a more general term which could refer to anything from paper to a VCD to something like this main memory. Now you will notice that I have opened up the space inside the CPU, leaving a lot of space for some additional boxes to be drawn, indicating that very soon I'm going to be mentioning some more of the components of a CPU. For the moment, we understand the ALU, arithmetic logic unit, control hardware, and the registers. Let me just quickly recap about the registers. Remember, there are general purpose registers and there are special purpose registers. Examples of the special purpose registers that we saw are the PC, the program counter, the IR, the instruction register, and the status register. The PC always contains the gives you the indication of from where in main memory the instruction which is currently being executed inside the processor came from. And the IR, or the instruction register, always contains the instruction which is currently being executed by the CPU. Then we have the general purpose registers, of which we saw there could be, let's say, 32 inside the processor. So when I talk about both special purpose and general purpose registers, I'm referring to this box over here. Now, one additional thing about general purpose registers which I'd like to mention at this point is, you'll remember that as far as the kinds of data that a program might have to execute with are concerned, we saw that there are different kinds of data. For example, there is data which is of integer type, and there's data which is of real type, and so on. So a question which may arise is, are all the different kinds of data going to be stored in the same registers? And in answer to this question, the designers of computers sometimes include separate registers to store integers and separate registers to store real values. Remember that the real values are represented using floating point representation. So the registers which are used to hold real values might be called floating point registers. So in some processors, you might find out that there are two collections of general purpose registers. One collection of general purpose registers in which integer data can be temporarily stored from memory, and another collection of general purpose registers into which floating point or real data can be temporarily stored from main memory. So there could be two or even more sets of general purpose registers. Okay. Now with this, let's move on to before moving on, let me just I may have raised your curiosity about what other boxes could there be in a CPU, what are the components. And two of the components that we're going to see more about later, one is the cache and one is something called the MMU, and we'll be seeing about them later. But this is what I had in mind in leaving some of the space blank in this diagram. Okay. Now let's next move on to the main memory. Let's learn more about main memory. We're actually not going to learn too much more about the processor for the moment. Once we know a little bit about main memory, we'll come back and talk about the operation of the processor a little bit more. Okay, so remember, the main memory is that block diagram. It's a form of memory in which the instructions and data of a program are stored. Now, the first thing which I'd like to point out is that we will view the main memory as being a sequence of locations, each of which is referred to by a unique memory address. So main memory is a sequence of locations. There is the first location, the second location, and so on. Each of these locations has a unique memory address, and we'll refer to the address of the first location as 0, since the memory addresses are typically assigned as unsigned integers. So the memory addresses will go from 0 on up. So if I have a memory which is of size, a main memory which is of size 4 gigabytes, then the first byte in the memory would be referred to by the address 0. The second byte would be referred to by the address 1, and so on, until the last byte, which would be referred to by an address which is something in the neighborhood of 4 billion. You'll have to calculate what 4G is. Remember that 4G is going to be 4 multiplied by 2 to the power of 30 and not 4 billion. So it's much higher than just 4 billion. Okay, now, so we view main memory as a sequence of locations. And remember that obviously these memory addresses are going to be important, because a given variable, like an integer variable x that my program uses, is going to have one memory location associated with it. And my program will refer to that variable by referring to that memory address or that memory location. So as a programmer, I may have to know something about memory addresses. Okay, now one term which is often used in connection with memory systems is the term byte addressable. And the idea here is, now I said that each memory location has an address. So if the size of each memory location is 1 byte, that would mean that each byte of memory has a unique memory address, and I would refer to that memory as byte addressable. You should note that it is conceivable that I could have a memory in which each collection of 4 bytes has a memory address. In other words, the size of a location might be 4 bytes. And this would make sense if all of my data was integral data, integers or floating points. But we know that typically the smallest data that you could work with, that we've talked about at least, is character data, and it is represented in 1 byte, and that there are lots of situations where programs have to manipulate character data. So it might make sense to actually have byte addressable memory, so that each byte of memory has a unique memory address. Okay, now this raises the question of what about a 32-bit floating point value? We saw that the real values are represented using the 32-bit IEEE 754 floating point representation. So that would mean that a single real or floating point value would occupy 4 memory locations, because it is 32 bits or 4 bytes in size. All that this would mean is that if I had a float x variable, a variable x which is declared as float of x, then it occupies 4 consecutive memory locations. Maybe memory location 16, followed by memory location 16, 17, 18, and 19. That might be the 32 bits in which the float value is represented. So that gives us some idea of how data items which are larger than 1 byte could have addresses associated with them. But this does, of course, raise an interesting question, and that is a question to which the answer is going to be byte ordering. But let me just frame the following question. Over here, what I have drawn for you to see, is a picture of a region of memory. So I'm showing you a number of memory locations. Right? So, and as you would guess, the number which is below the value which is in color is the address of the memory location. Since each of the pieces of data in the memory is of size 1 byte, I've shown each of the memory locations as being of size 1 byte, and I'm referring to the address of that location as its byte address. So this is the memory address. So the memory addresses are shown in decimal. There is memory address 400 up to memory address 407. And I'm not showing you all of memory. So memory obviously starts from memory address 0 to the extreme left, going up to memory address, a large memory address at the right side. Now next you'll be wondering, in that 1 byte, the first byte, the byte which has an address of 400, I have shown a value, but I have written it as 1A. By now many of you would have guessed that I'm showing the values in hexadecimal. Remember, the hexadecimal is the base 16 number system. In the base 16 number system, there are 16 different digits. They are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. F stands for 15. And therefore, it takes 4 bits to represent 1 hexadecimal digit. Therefore, in each of these boxes, each of these memory locations, I am showing you 2 hexadecimal digits, which means that each of them is of size 4 bits, and the size of the 2 digits together is 8 bits or 1 byte. So I'm showing you 1 byte of information encoded in hexadecimal. All right, so that's what this example is showing. It's showing you a picture of a window out of a main memory between addresses 400 and address 407. Okay, now the question which I'm going to ask is, what is the value of the unsigned integer at address 400? Okay. So this is actually an interesting question, because as it happens, it's easy for us to understand that when I talk about the address 400, as I had mentioned earlier, I know that the unsigned integer is of size 4 bytes, which means that it's going to occupy the main memory from address 400 up to 403. So that we know from what I mentioned a few minutes ago. But now I have the question of trying to interpret the byte sequence 1A, C8, B2, 4, 6 as an unsigned integer. Now as it happens, the answer to this question is that there are a few possibilities of what the value of this unsigned integer is. Now let me just mention what 2 of these possibilities are. Now one of the possibilities, and I'm sorry, these 2 possibilities depend on the significance that I associate with these bytes. I used the term significance in a previous lecture when I talked about a least significant bit, the bit which has the least weightage associated with it as far as its contribution to the value. And the most significant bit as being the bit which has the most weightage associated with it in terms of its contribution to the overall value. So very clearly there are going to be a few possibilities as to how I could order these bytes in terms of their significance, which is why we have the title of this slide, byte ordering. Okay, now here's the situation that we have. We have 4 bytes in memory, and the question is, what is the value, the unsigned integer value of the 4-byte quantity at address 400? In other words, the address which occupies bytes 400, 401, 402, 403. Now one of the possible answers to this question is that I could view byte 400, in other words the value 1a, as the most significant byte. It is the byte which contributes the most to the value. In other words, it is the most significant, it contains the most significant bits of the 32-bit unsigned int. So if this is the case, then the 1a C8 B2 46 has 1 as the most significant byte and 6 as the least significant byte. I can expand each of these hexadecimal digits into binary using the binary hexadecimal to binary lookup table, which I won't show it to you, but hopefully by now you all remember that 1 will map to 0, 0, 0, 1, a will map to 10, which is 1, 0, 1, 0, and so on. So I'll end up with this 32-bit quantity. So this is the 32, under the assumption that 1a is the most significant byte, the unsigned integer at address 400 will have this binary value. These are the 32 bits of the value, where this 0 is the most significant bit and this 0 is the least significant bit. I can now evaluate this unsigned int using the binary, using this summation, the summation from I equals 0 to n minus 1, where n is equal to 32, x sub I multiplied by 2 to the power I, and what I come up with is the value 449,360,454. So under this assumption, the assumption that 1a is the most significant byte, the answer to my question is this value, 449,360,454. This is only one possibility. And this convention, where I assume that the byte, which is the address deciding byte, here I was talking about the integer at address 400. And if my convention is that the byte at 400 is the most significant byte, then this is called the big endian assumption about byte ordering. Now there is obviously at least one other possibility, and in that possibility I view not 1a as the most significant byte, but I view 46 as the most significant byte. Okay, so I'm talking about the integer at address 400, but I view 46 as the most significant byte, which means that 46, B2, C8, and 1a are the bytes in order of significance. 4 ends up being the most significant hexadecimal digit, a ends up being the least significant hexadecimal digit. And once again I could expand this into binary using the hexadecimal to binary table. I come up with this value. Once again I can evaluate this as using the summation, and I come up with an unsigned integer value which is different from the first value. So remember, this was what happened if I assumed that the bytes were ordered with the byte which defines the beginning as being the least significant byte. And this convention is known as the little endian byte ordering. So once again, this is just a convention, and I could build a computer which uses either of these conventions. You may be a little curious as to where these terms little endian and big endian came from. As it happens, this is a somewhat recent development. It was, I think, something that happened sometime in the 1980s, this terminology, but it's basically derived from a book in which, in fact, Gulliver's Travels. Okay, so with this, the question that you might ask is, I talked about these two possibilities. Are there any others? And technically, you might say that where there are 4 bytes, the 4 bytes can be ordered in many other ways. For example, I could arbitrarily say that this is 402 is the most significant byte, 403 is second most significant, 400 is third most significant, and 401 is the least significant byte. So there are various other possible byte orderings, but the two most frequently used byte orderings are the little endian and the big endian byte orderings. So you will note that these two are different. They result in different interpretations of the value, the unsigned integer value at address 400. Under the big endian byte ordering, for this picture of memory, the value was 449 million plus, whereas under the little endian byte ordering, the value was much more. And as I had mentioned, I could build a machine which uses the big endian byte ordering convention, and somebody else might build a machine which uses the little endian byte ordering convention. And the question to us as programmers then is, does this affect us? Is this something that we should be concerned about? Now the answer to this question is that if you are just writing programs to run on one machine, then this is actually not a concern to you at all, because your program will run on that machine, and whether internally big endian big endian ordering is used or little endian ordering is used, it doesn't matter, because all values will be interpreted using the same convention. But there can be scenarios in which this is relevant to the programmer, and let me just quickly describe one which we will be encountering much later in this course when we talk about parallel programming. Now in parallel programming, I write a program in such a way that it runs in part on one processor and in part on another processor. In other words, I divide the computation so that it runs on more than one processor, and the two parts of the program may have to interact. Now if one of the processors is using big endian byte ordering and the other one is using little endian byte ordering, then I may end up having a little bit of a problem. Or let me describe this to you in another way. Let's suppose that I have a program which is written to execute on a collection of computers on a network, and that some of the computers on the network use little endian byte ordering and some of the others use big endian byte ordering. Then once again, if I have a program which is running across more than one processor, then this may end up being something that I have to be worried about. Now in one of the previous lectures, I had given this idea that often it is possible to write a program, an experimental program, to run an experiment on a computer that you have in order to learn a little bit more about that computer. And this is clearly in a situation where one could try such an experiment. So the question that arises is, you have a desktop or a laptop computer with you, and now that you've learned about this concept of little endian and big endian ordering, you may be wondering, does my laptop or desktop use little endian ordering or big endian ordering? And one way to find out would be to look up the manual or to read about the processor, read about the details of that particular processor on the internet or something of that kind through a manual. But a more direct mechanism would be for you to try to write a program, a small C program, which could determine whether the machine on which it is running uses big endian byte ordering or little endian byte ordering. And with a little bit of thought, you realize that this may not be that difficult. Let me just give you a rough idea. Let's suppose that I have a signed integer. Right? So I know that the signed integer possibly occupies 4 bytes of memory. In other words, it is of size 4 bytes if it is a 32-bit integer. So if it is a signed integer and I know that it is represented using the 2's complement representation, then I would know what to expect in terms of the most significant byte. Therefore, if I wrote a program in which there was a declared signed integer variable x, and then I put, let's say, the value -1 or -3 into that variable using an assignment operation, and then in the rest of that program I examined the 4 bytes at the address associated with that variable x, then I could actually figure out whether the bytes are being interpreted in little endian or big endian fashion. So a program could be written to determine whether the machine on which it is running uses little endian or big endian byte ordering. Now another fact which I will just mention at this point in time is the following. Many of the processors which are made today are actually designed so that the choice of whether they use little endian or big endian byte ordering can be changed. In other words, they are configurable. So somebody who is knowledgeable enough could actually reconfigure the processor so that the next time that it is booted up, it actually uses the opposite byte ordering of what it was using. Today it might use little endian byte ordering, and a few days later it might use big endian byte ordering. So this possibility is also there. Processors which can be configured to use either little endian or big endian byte ordering. Right. Now with this we have, in this lecture, I will just quickly wrap up for today. What we have seen is that the components of the computer system, largely the processor, the memory, and the I/O devices. We spent a little bit of time looking at the processor in more detail. We understood that the control hardware is hardware that manages the execution of instructions. The ALU is circuitry that can do arithmetic and logical operations. Registers are both either general purpose or special purpose. The special purpose registers are used for very specific activities by the control hardware. They are not available to the programmer for direct use, whereas the general purpose registers are available to the programmer or on the programmer's behalf to the compiler for using frequently accessed variables. And this might be important because of the large speed disparity between the main memory, where the instructions and data are stored, and the processor, where the instructions are executed. We saw more about memory, the different kinds of memory that are present in a computer system. And finally, we spent some time looking at the mechanics of main memory, where main memory we view as being a sequence of memory locations, where each memory location has an address, which is an unsigned integer. And we understood the notions of byte ordering in terms of being either little endian or big endian. Thank you.